Alright, welcome back, chemistry kids. This is Mrs. O'Neill. I'm just going to be reading through my notes to help present the information to you guys in that way that we're so familiar with. I only plan to do these screencasts probably on Tuesdays and Thursdays to go with the notes, but hopefully this will help those of you who like hearing all the little extraneous details that I tend to throw in, or if you're just more of an auditory learner compared to a visual learner and you like hearing the notes instead of just reading them on the paper. You should all have your notes printed out already as well. But I'll also post the individual days worth of notes every day that we do notes on Tuesdays and Thursdays, as well as these videos. Anyway, so we're starting Unit 6 today. Unit 6 is going to be about liquids and gases. This is going to be the last unit that we do this year, and fortunately it is actually much easier than the thermochemistry unit that we just finished or the stoichiometry unit before that. We'll still be applying some of the stuff that we learned, like how to do moles and grams conversions and some of the road mapping and multiple conversion layouts, but for the most part the formulas in this unit are a lot easier. I've also sort of pulled it together out of two separate units, and so it's a little bit disjointed. That's why it's liquids and gases, not just liquids. Usually we go into a bit more detail, and there's some stuff that we're not going to do this year simply because of the sort of the situation that we're in. But we're going to make the most of it and still learn a lot. Today we're just going to talk about water though. 6.1, water. Water is awesome. Water is the coolest thing ever, basically. It's got all sorts of cool chemical properties. It is an underlying component of like a lot of what we do. A lot of our solutions and stuff like that involve water. This isn't working very well. What is it doing? We'll pretend that didn't happen. Okay. Also, I'm not going to edit these very much, so unless I, say something really inappropriate for school, I don't plan on editing this. You'll get to see all the weirdness, just like in real class. But okay, so water. We already know water is all over the planet. 70% of the surface of our world is water. And something like 50% of people live within 10 miles of the coastline, which is fairly ridiculous, but since we're here in Kansas, it doesn't seem that way. But if you ever travel to the coastal cities, they are tremendous. And the population density, even outside the big cities, is so much higher compared to here in Kansas. It's just sort of the way it is. Water is a unique compound in that it occurs in all three phases here on Earth. We call that being triphasic. It's a solid, a liquid, and a gas all at the same time at different locations on our planet. It is also a polar molecule, and we've already talked about polarity quite a bit. Polarity is having those positive and negative charges, like our little diagram here. Eek, that's totally what I was trying to accomplish. So the O is just a little bit negative, and the H's are a little bit positive. These aren't full-blown plus ones or minus ones, but they are more like 0.01 or something, but it gives it a little bit of stickiness. It lets them lock together like magnets, and that determines a lot of their the characteristics are based on this polarity. Okay, the attraction between those molecules is called hydrogen bonding, which is a terrible name because it doesn't necessarily involve hydrogen. It just has to involve these partial positive and negative charges. In water, this occurs between I just noticed it's falling off the edge there. That's not good. Let me see if I can fix that. Maybe I have to change my zoom. Sorry, guys. Not quite that big, maybe. This is all very experimental for me, too. There we go. Alright, we'll work with that. Okay, so, anyway, these temporary, fairly weak little bonds are called hydrogen bonds. They help hold the water molecules together, but they also can be broken easily, so that's why, even though liquid water is kind of sticky, you can still break it into chunks with little drips everywhere. It's not so strong like crazy strong magnets strong, but it's still an important piece. Anything else that's polar, like salt or other ionic compounds, can also mix easily and dissolve in water. A lot of molecules fit this definition, which is why we call water the universal solvent. It can dissolve most anything. Not everything, because non-polar materials won't dissolve, things like oils and waxes and stuff like that, but polar molecules will. That makes water the foundation to a lot of our chemistry. Anytime we dissolve things into water and create solutions, it's also the foundation of our biochemistry. Our own bodies are made primarily out of water. By some estimations, we might be as much as 75% water by mass. Maybe 90%. I don't remember. I should probably look that up. But anyway. So, the other thing that hydrogen bonding can cause is surface tension. The water molecules are all attracted to each other, and as long as there are water all around, each individual water molecule is pulled in every single direction. It's not like a 1-to-1 ratio. It's not attracted to just the water molecule on its left. If it's surrounded by water molecules, it's pulled every which way and it stays sort of in balance, being pulled in all those different directions. However, if the water molecule is at the outer edge of the droplet, now it's only got water molecules on one side and air on the other, and it's not going to have the hydrogen bonding with air. And so it's getting pulled inwards towards the middle of the droplet, and it doesn't have a balancing pull outwards. This creates motion, basically, and it pulls in all those outermost edges just a little bit tighter compared to the water itself. It makes like a slightly denser area right along the edges of the water droplets. We call that the surface tension, where there's sort of like a thicker skin on the water. And like I said, it's caused by that unbalanced attraction. It's helping the water droplets minimize surface area. If you had water in zero gravity, it actually forms perfect little spheres, which has the most volume with the least amount of surface area. It's actually the same reason that our planets are spherical. Except for planets, it's gravity, and for the water droplets, it's the surface tension. There are chemicals that can reduce surface tension. We call those surfactants. These are mostly soaps, and they're really important to help break up the stuff that water doesn't like to mix with, because if the surface tension is high enough, it actually repels the things that aren't water, like having bugs that can walk on the surface of the water or leaves that float on the top. It's because the surface tension is actually holding it up. But if you break the surface tension down, now those things fall right in. We use these to clean, because if we're trying to clean up greasy mixes, the water does not want to pick up the grease particles. It's not having the hydrogen bonds because grease is nonpolar. But the surfactant reduces the surface tension, and now the water droplets can move around and absorb the grease molecules and encapsulate them. And then as you rinse your pots and pans, the grease can flow right off with the rest of the water and go down the drain. So we use them a lot in cleaning. And we've seen the effect of surfactants as well, and the changes in surface tension when you do that pepper trick in our chemistry magic show, where you have a scattering of pepper on the surface of the water, and you like dip a finger in soap, and then you touch the water, and the pepper suddenly gets just yanked to the sides. It just clears out the middle right around where you touched. That's because there's still surface tension at the edges of the plate where the soap hasn't had any effect, but there's much less surface tension in the center of the dish now, and so the edges of the plate yank the pepper molecules out to the sides, or pepper particles, and just yank it all the way out of the center. Okay, so water being sticky is called cohesion. We don't tend to think of water as a sticky material because we think of it as a cleaner. We use water to cleanse ourselves, and so thinking of it as something that's like sticky, like jam or honey or something, just seems weird. But water is actually terribly sticky. There's a reason why when you stand up in the tub of water, it doesn't just like sluice right off you and leave you dry as a bone. It sticks to your skin, and you actually have to get a towel and rub it off. That's because of the cohesion. The hydrogen bonding makes the water sticky. It also allows water to sort of climb up through narrow tubes. It's kind of like that game of like the monkeys. I don't know, this is very old school, but where the monkeys stick to each other and then they pull each other up. Water molecules do the same thing. They're pulling up the other water molecules as they move, and so it'll rise up through thin straws, up through the narrow spaces in plants. That's how plants move the water up and down through their stem, even through the tiny little pores of like paper towels and stuff like that is the same thing. This is all called capillary motion or capillary action. Water can also stick to things that are not water. This is adhesion. It just has to be polar. So when the water's sticking to you, that's adhesion, because your skin's not just water. Okay, another important thing, because water is so sticky, it doesn't like to change phase very easily. Liquid water does not want to release the other water molecules and let them turn into a gas. And so the vapor pressure, which is the pressure of the gas molecules above the liquid surface of like a puddle, is very, very low. Water is slow to evaporate. It takes a lot of energy. It has to absorb sunshine, or it has to have a high ambient temperature. It has to be a hot day outside. But if it's at all milder, it's not going to evaporate quickly. This is super important, because if water evaporated the same way like rubbing alcohol does, where it just whoosh, is just gone, we wouldn't be able to have puddles and lakes and oceans, because all the water would be in a gaseous phase. We'd have tons and tons of humidity, muggy weather everywhere, but the liquid water on the surface would be much, much less available. Okay, and then finally, water also is just weird when it forms solids. This doesn't do so much to hydrogen bonding like everything else we've been talking about. This is mostly just because of the molecular arrangement of the atoms. When they're trying to lock together to form a solid, they just do it at odd angles, and they stick out more, and it takes up more space. Solid water does not have very tightly packed particles. It has like a wide lattice of particles instead. And so as a solid, it's actually less dense than a liquid, and that's very unusual. Most things are more dense as a solid. They'll sink if you put it in a liquid form of itself, but the liquid water just stays underneath the solid water. Solid water floats on top. And it's very strange, but it's also very important, because if solid water, ice, sank as it froze, then our lakes and rivers and stuff like that would freeze from the bottom up every year instead of from the top down. And if it froze from the bottom up, there'd be no place for the fishes and stuff to go. And anytime it froze solid, it would be just a mass extinction event for whatever was in that body of water. Same thing with like Antarctica and the ice caps. If that ice was sinking as it froze, eventually it would fill up the Arctic Ocean or the Antarctic Ocean. And there would be a ton of ice at the bottom of the oceans where it's very, very cold all the time, and it would never melt. And that would be a real problem. And so having solid water flow is very, very strange, but also very, very important for life here on Earth. Okay, sort of going with that. Water also has extremely high heat capacity. It's slow to change temperature. It takes forever to boil pot. It takes so long, it's actually like a cliche, you know, watch pot never boils. It just takes forever. It absorbs a lot of energy and gets very little temperature change out of it. This makes it slow to change temperature, which is helpful for stabilizing the Earth's climate. Our oceans and lakes and stuff like that don't heat up and cool off very much, and so the surrounding land doesn't heat up or cool off as much compared to like the inside of a continent. We actually know what it's like not to have those large bodies of water around, because inside of continents have extreme temperature changes. We could have very, very hot summers and very, very cold winters compared to some place like San Francisco or shoot, I was trying to think of an East Coast city in the same latitude. Nothing's really coming to mind. I'm not that familiar with the East Coast, I guess. But their temperature extremes are just not as high compared to like central Kansas, where you can get these really hot summers, really cold winters, and it all has to do with proximity to the oceans. And it also helps us maintain our body temperatures. If the water inside of us didn't help keep our temperature the same, we'd have ups and downs. We'd have to spend a lot more energy trying to maintain our body temperatures. We already spend a lot of energy for that reason, but not all of it. Okay, that's the end of the notes for today. I hope me reading it and my sort of meandering might have helped. You don't have to watch these videos. They're completely optional, but I am just trying to help you guys get through this very, very strange situation we've all found ourselves in. I'll be posting more videos, screencasts, on Tuesdays and Thursdays to go with the notes as we move through this unit. Thanks for your time. Have a great day.